Thanks. So, the thesis of my talk today is that there are lots of different ways to do search. We're going to see a whole variety of them, but I need to amend this statement because there are lots of wrong ways to do search. So who am I, you might be asking? Who dares say that I'm doing search wrong? My name is Daniel Lindsley. I run a small web consultancy that is in the process of shutting down, so if you need anybody, please let me know. I am a longtime Pythonista and more recently known for what I do in Django. I spend lots of time writing all kinds of different Python things, so it's not just Django apps, but it's what people know me for. I'm the author of 2 applications called Haystack and TastyPy, both of which are Django third-party libraries, but we're not going to talk much about Django today. Instead, we're going to try and attack search from a broader Python perspective. So, what you should know most of all is that I really get excited about search. I love search technology and RESTful APIs, but that's a whole different talk. So the most important thing you can do is to pick the right approach when you attack your search problem. There are a whole diverse world of different possibilities of how much you may need to handle or do, or what function your search feeds into. So picking the right approach makes more of an impact than anything else I'll say in the rest of this talk. And there are things that I'll say about higher-end search that may not apply to your use case, and so feel free to ignore them. So, some considerations, or maybe not. Nope, no considerations. Okay, things you want to be thinking about when you start tackling adding search to a product or to an application or to something else. You want to think about the frequency of use. Are you going to be serving thousands of people a day? Is it just client software and only one person is ever running a search query at a time? Are you doing millions of search queries a day? Having a good gauge on how much load you're going to be placing on your search functionality matters a whole lot in what you pick. Similarly, you want to be thinking about the intended usages. Is search core to what people are doing? Is it the only way to navigate a huge mound of data? Or is it something that's more of an afterthought? Is there navigation in place in the application that already takes care of whatever they need? You want to be thinking about the amount of data. Are you going to have tens of records, thousands of records, millions of records? This greatly affects what choice you make, as well as storage considerations, because each one of those records takes up space. If you have very small records, say for instance, you're just storing tweets, that's a very small finite string with lots of documents. Whereas if you're storing a big corpus of, say, a library or some huge pile of business documents or something else, you're going to have much more space taken up, and it's just a multiplier on how many records you have. And the last thing you want to be thinking about is what is the CPU cost to be running this kind of a search query? If it's relatively simple, easy queries, it may not be so bad. If they're running very complex things to do some higher-end analysis, then you really need to make some space. So I'm going to make some assumptions about you, dear audience. I assume, one, that you know Python. I'm going to hope that's not a big stretch. I'm going to also assume that you know just a little bit about SQL and about I/O, just enough to know that, hey, if I kind of know how SQL queries are structured, and hey, I/O takes reading a file off the file system. I'm going to assume that you can kind of figure out words like tokenize, and I'll try and explain some of the other search terminology I use as I go. But if I'm saying something crazy, you should definitely call me out. And I'm going to assume that you want to make your search even better. If you're happy with how things are right now, then don't change it. So, I'm going to warn you. I'm going to say some very hurtful things in a second here, as politely as I can. But know that all of us have been there, well, unless you're Guido, and that this is a process. It's all about making things better as you go. So, without further ado, I want all of you to take a deep breath and steel yourselves for the worst code you'll see yet. It doesn't look so bad, does it? It's kind of innocuous. It's just nice Python. Well, there's some issues with doing this kind of an approach to search. First of all, we're collecting what's presumably a list of file paths, and we're opening them all and reading them all into memory. And then we're taking all those things that we just read into memory and literally doing substrings to find the search query. Looks really innocuous, but takes tons of RAM, tons of I/O weight, and really is just about the most inefficient way you can do anything. So, we covered the worst. It only gets better from here. It only gets better. Slightly less wrong, but please still don't do this. I don't... Now, mind you, I wrote lines like this, plenty of them. What's wrong about this? I mean, you're using what's built into SQL. This is nicely formed SQL syntax. Pretty much every engine supports this. A couple things. First of all, when you do things like I like or like, and especially with wildcards, you introduce table scans. And if you've done any kind of database tuning, you know what a table scan means. It means you're taking every single row in that table and reading it in. So basically, a query like this will be just about the most inefficient thing your database server has done all day. Also, wildcarding like this hurts terribly. And as soon as you introduce more complex queries, you're only going to get things that neatly match. So please don't do this. Please. Still wrong. I don't know what to do for you if you do this. I would suggest mental help, maybe counseling. No, it's not that bad, but things that are wrong with this. First of all, we're using grep, so we're doing something that's already external. We're depending on something being installed correctly and present on a system. And yeah, if you're using a Unix, yeah, you're fine. But we're also calling out and making another process, and then you're having to parse whatever comes back out of grep, which can change between different versions of grep. Your life will be hell. Please don't do this. Exactly. Paralyzed. I love it. So some commonalities between the wrong approaches. The good news is we're done with wrong. We're going to get better. The commonalities that you're probably noticing is that we're reading everything into RAM. We're reading huge amounts of data in. And if you can imagine a corpus, a collection of documents that's gigabytes in size, reading in gigabytes at a time just is not a good way to do a query. Similarly, all of these approaches are basically looking for a substring. They're taking one big string and going, hey, is it at this position? Nope. Next. 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 It's very slow. So that's very inefficient. And this is happening on every single query. The database engine isn't caching that I like. There's nothing it can do with that. And similarly, if you're just funneling everything through grep, yeah, grep loads things nicely as like streams of data off the hard disk, but it's still going to eat through all those gigs every time you do it. So we need something better. And what's common in the search world is this idea of the inverted index. You can think of an inverted index kind of like a Python dictionary. What it basically does is you take all of the unique terms that appear in your entire corpus, all your documents, and they basically become keys of this essentially dictionary or hash lookup. And what you can do then is you'll find that these engines then proceed to map where those terms were found in these documents. This is really simple. We have just document 1, which you can imagine is hello world and other standard introductory fare, and document 2. And the only thing that's consistent between these two is the term world. But in an inverted index, world gets stored just once, and then it proceeds to store document information. Now, in a more complex engine, you'll find things like term vectors and positions. You'll find other bits of data, metadata that are stored. But for all intents and purposes, this is how almost every good search engine works. And it works because you can take words like world, and you just do a hash lookup. And a hash lookup is a lot faster than searching through a substring of a gigabyte file. So let's talk about something that's better, but still pretty bad. We're going to go back to pure Python. We like Python. This is good. We're going to basically just build what we saw on the previous slide, but we're going to build it dynamically out of a collection of files. We have a global index dictionary. We run through our files the same way we did before. We still have to read them all in, but this time we're going to split them and make a set so that we only have the unique terms. And then we're going to try and set those up in the dictionary and map them to the file that they were seen in. And then later on in our code, we run an index.get on our query, or if you have something more complex, you do multiple gets. Now, this is all well and good because it is better. It's better than every single query reading in everything all at once. But there's lots of things that still aren't great about this approach. Sorry. Some bad things. First of all, we have some really ugly global state. If you want to use this index anywhere, you've got to import from the top of your module, and who knows if it's prepared yet or anything else. This is not the greatest way to run a query, especially if you're used to things like Google or Bing or something similar to that. This sucks. And this really isn't that intelligent with the way it handles terms. So things like bananas will be different than the term banana. Search engines usually include functionality called stemming to find root words and storing just root words to find things. But this really doesn't fit a bunch of approaches. So let's talk about something that's just a little bit better than this. There is a library out on PyPy, or if you use Crate, called microsearch. It was written by yours truly for a different talk also on search. And it's strictly a basically kind of tutorial piece of software. You go read the source, and you can see lots of the big things, bigger picture things that play into how search functions. It's better than our previous approaches because it does use less RAM. We're not, flooding things up with lots of long strings. The index is persistent, so we're not rebuilding every time a process starts, but instead working with something we've already built up. And it has some better query facilities. But it's still inefficient, it's still slow because it's pure Python, and it's really, really I/O heavy. So please don't use this in production. If you want to learn, great. Don't deploy this. So let's talk about something that's actually good. Something that's actually good is a library called Whoosh. Again, pure Python. You can pip install it, and that's pretty much all the setup you have to do. And it works off file system access. So indexing is a little bit more complex than what we've looked at, but we basically just define a schema which has one single field in it that is a text field. You can think of this much akin to like a database schema that has just a blob. And then we create the index itself, and then we get a writer object off the index, and we just add in some documents with some content and commit them. Pretty straightforward, relatively simple, more than we've seen so far, but easy-ish. Searching is equally easy. If we have that index from the previous slide, where we created it, we can use that to get a searcher off that index. And we just say, hey, we're only interested in the content field. Here's the schema that we want to talking about, and please parse this query. In this case, we're searching for first, but we could be searching for world or anything else. We tell this, now this just builds up a query. We then tell the searcher to take this built-up query and perform a search on it, and we get some results back. Whoosh is great because it's way better at querying than anything we've seen thus far. It can handle much more complex queries. It's analogous to literally searching for a string in a big blob of text as it would be to moving to something like SQL and searching through rows and having lots of much more fine-grained control over what you're searching for. It is, in fact, faster than everything else we've seen thus far because the code has been optimized to be good at loading and doing search. And it has many more features than anything we've seen. But it's still really slow, and it's still really Python. And we love Python, but maybe it's not the best thing to be using to actually build core search functionality. So, moving up in the world, we're going to move on to Zapier. I don't have a code sample for this because I don't have a current local environment for it, but it has decent Python bindings. It's pretty quick because the underlying library is written in C++, and has a really nice feature set with good querying. All the features we kind of want, but it does require file system access, so if you're deploying to a large number of servers, or you have some kind of distributed setup, or you can't write to the file system, not a good solution. And it expects, much like Whoosh did on one of the previous slides, it expects a structured query object. So if you have users who are used to just typing something into a box and hitting enter, it's not going to be as convenient for them, and you're going to have to invent parsing things to build up the right kind of query object. So a little bit more, excuse me, a little bit more painful on that front, but really an order of magnitude faster than what we were talking about before. So let's talk about something that's pretty freaking good. Solr is, in fact, pretty freaking good. And because we don't want to completely abandon Python, we have some nice Python bindings called PySolr that are installable. And PySolr has a very nice API for working with documents. We simply point it at a stood-up Solr instance. We say, hey, we've got a document called document1. It's got this text blob. Please add it. When it's done being added, we can then search on it. It has much more than this, but this is the most basic kind of build something and search on it example. Solr is great because it is really, really fast. We're talking about still an order of magnitude faster than we were before. So we've gone from extremely slow Python code that runs in seconds to Whoosh, which runs in maybe half a second, to Zapier, which runs in even less than that, and now down to Solr, which runs even faster. It also has just a boatload of features because it's built on top of a technology called Lucene. Lucene is a collection of Java-based search libraries that basically can be used to compose something bigger or just to implement directly. And it has good query support. Now, why you don't want to use this? XML. Oh God, I hate XML. I hate XML so much. And everything is XML. It's XML all the way down. It's painful a little bit, but once you hit a certain stride with it, it's really not too bad. And you can kind of, once you're starting to work with the Python bindings and you have it configured, you can kind of just turn a blind eye to what's going on and how it's configured. Where Solr tends to fall down is once you start talking about having millions of people running queries at a time and huge indexes, distributed setups really kind of hurt. It's good for just a master, good for master-slave, kind of master-slave-slave. As soon as you start adding more slaves, you're going to start having more and more pain and suffering. And eventually, as soon as you need multiple masters, just cry. It's Java, so you don't have any RAM left when you're done running it. I'm sorry. And you do need a server. This is the first time where we're talking about something in Python that you can't just be installing, at least easily. Oh God, locally installed Solr. You can't just be easily installing this on a client machine. You really need something stood up, hanging out on the internet someplace. So, the very best. We were really happy with Solr. It was pretty great for what it was. But the best is Elasticsearch. Elasticsearch is a relative newcomer to search, the field of search technologies. It also has a nice Python binding called PyElasticsearch. There is another Python binding called PyES. I recommend that less. It's harder to deal with, doesn't always pass tests, doesn't always actually work release to release. Sorry, I like staple software. But PyElasticsearch, really easy. Looks a ton like the Solr example that we had. We import this Elasticsearch instance. We point it at a setup box that's listening on a relatively RESTful API. And we just index some content. We throw in a document. We tell it what index we want to put it in, what bucket it applies to, and the document ID. And then we can search on it. Pretty straightforward, relatively speaking. Elasticsearch is the best because it's all the good things that we had in Solr, plus it has, because it's built, again, on Lucene. It's all these same technologies, just presented in a slightly different interface or server. But it has a great ops story. I can't say enough about how easy it is and how little of a nightmare it is to run a cluster of Elasticsearch boxes, because you will not hate your life. You say, up goes the box. Install Elasticsearch, and then you say Elasticsearch join cluster, ding. And just like a pianist on a piano, you hit that last note, and it joins, and it redistributes data, and you don't think about it anymore. Done. And I'm guilty of laziness as a programmer. So, and no XML. We got rid of XML. Yes. Wait, they use YAML. Only slightly better. But frequently what you'll find actually is both Solr and Elasticsearch expose themselves over the web, so they act like regular web endpoints. You post to them to send a document. You do a get to pull stuff out. And Elasticsearch takes it one step further and acts like a full, proper RESTful server, responding to things like puts and deletes, and doing things just a little bit nicer than the way Solr works. And we get JSON back by default. So all good things. Unfortunately, it's still Java. The memorial service for your RAM will be held after this talk. And really, Elasticsearch is okay on a single box, not really any more better. Hi, I'm Daniel. I'm the stupid American. Not really any better or worse than Solr on one big box, but as soon as you spin up a cluster, they form basically kind of a dynamo-like ring, and they start distributing both data and queries across all the boxes so that they can handle much more load in aggregate than a single master server with some read slaves. So Elasticsearch really starts to shine as soon as you have like 3 or 4 boxes spun up. So regardless of which thing you choose, and please choose one of the last couple that we've talked about, here's some things that you really want to be thinking about when implementing search. It flies in the face of everything every good programmer knows about how a schema ought to be. You denormalize. You denormalize, you denormalize, you denormalize, and then when you're all done with that, you denormalize a little more. Really, if you have any kind of relational data, relations don't really work in search engines because they're used to being documents. They're kind of like the original NoSQL stores before it was cool. And so what you find is that if you have things that would be related, like you would be doing a join in a database or something, what you actually want to be doing is you want to be denormalizing onto that main object. A classic case of this is you have some kind of a post, like a blog post or something like that, and you also want to index comments. And you have people commenting on this blog post, and you want people who said something down here in the comments to bring up this blog entry so that people can see the context in which it occurred. Well, what you do is you actually shove those comments onto that main blog post's document when indexing it. And that feels really counterintuitive. It feels really gross as somebody who's trying to optimize everything away, but it makes life so much better. So denormalize, denormalize, and then do it some more. Adding on fields for narrowing. A lot of people start out with search and they just do, okay, my boss said I just have to get this thing working in search. We're just going to index this main chunk of content, and I'm done. Yes. And then 2 weeks later, they're like, we kind of would like to be able to search by who posted the blog post. And you're like, oh, and by date. Can we get by date too? And while we're at it, it sure would be great if in our admin area you could see stuff that wasn't posted yet and search on that too. And eventually, the feature list starts growing and growing and growing and growing. Some ways that you can accommodate that is to add on additional fields to your documents. So with a little bit of foresight and planning, you say, hey, I expect that these kinds of patterns are going to emerge from search. We are going to have people searching by author. We are going to search by category. We do care about dates and if it's published or not. And what you can do is much like you would with a database model or schema or row, whatever your flavor du jour is, you add on extra data onto these indexes and into these documents so that you can, using those advanced query facilities, narrow down by those things as part of your query. Good search needs good content. If you take nothing else away from this talk, I want you to just ignore everything else I said. This is the biggest, most important thing I will talk about this entire time. It's the classic computing principle of garbage in, garbage out. And it applies even more so in the field of search. If you don't have clean, nice content, the engine is going to throw crazy results back because it's doing lots of post-processing on the content you send it. And so if you send it malformed content, you may find crazy, weird results start popping up because of how things were processed. So you want to make sure that you're thinking about, what are you feeding in? Am I feeding in a bunch of HTML soup that isn't going to do any good? Or am I feeding in just the plain, clean text that I need? You want to feed the beast. Even if you're not using the JVM, you want to have RAM on whatever is running the search queries, because it does take memory to use, and it takes more than you think it's going to. Lots of the search engines try to do intelligent things like only loading the indexes that are necessary for a query, or they do lots of internal caching if it's Solr or Elasticsearch, but it still takes a lot of RAM. It's RAM intensive. And another thing, especially if you are working in the web world, but pretty much regardless, you want to be updating these documents out of process, because it is doing all this kind of heavy post-processing on what you're sending it. You want to make sure that you're not blocking the user on indexing this thing. Because if the user just handed it a 17,000 word, here's my PhD thesis, you don't want to have them sit there and wait for it to go through everything and stem everything, lowercase, stop a word, tokenize, etc. You want to say, hey, we're cool, we've stored the data, you're good to go, and out of process, we're going to go update this. And the same things apply if you have something that's a client piece of software. You're going to be updating things probably in a different thread or maybe in a different process. So, where are we? Our queries are now fast, so much faster than loading gigs and gigs and gigs and waiting seconds and seconds and seconds. Now things come back in 300 milliseconds or less, more like 50 milliseconds if it's fast. We're sipping RAM. We're not eating up 4 gig of RAM when we read in our corpus. We're using maybe 60 meg. And our I/O is tons better because we're not reading in all that data. We're loading up a tiny, structured, or relatively tiny, structured index that we've been persisting over time and gardening. And we've got great documents that are going in. So, we're done, right? Huh? This handles all the technical aspects of search, but it doesn't solve the fact that search by nature is a user interface. Whether we programmers want to just wash our hands clean of this, we don't want to think about it, that's some other designer's job, please go away. But really, search comes down to a very simple process that goes around. So, I want to tell this in the form of a small story. In the beginning, long, long ago, wild search queries roamed the earth. And there was man and woman. Man, seeing these wild search queries, created links, and they were crap. Woman, seeing this, decided that highlighting would be much better. There would be context, and it was good. Man, seeing woman's fine highlighted text, got a bit jealous and decided to introduce advanced query syntax. Yes. Woman, sadly realizing that man was serious and feeling bad for him, introduced faceting. Man was in awe. Man, trying to reclaim what little dignity he had left, introduced spelling suggestions. Woman, having the chance to once again one-up man, introduced autocomplete. God, seeing this whole contest was pointless, decided that he would hand you your search results before you finished deciding what you were going to search on. Well, the good news is that my crazy little parable is all actually very easily implementable by all of you. Well, except for being God. So yeah, pick whoosh or better, and all of these things are possible. I'm going to demonstrate with PySolr just for brevity, just because if I did it with whoosh, it would be this long per slide. And I think we got enough of that earlier. So as we saw before, just simple results are pretty straightforward. We open up a connection to the to the Solr server, we do a query, and we get some results back. Now, this results object we get back is a collection. It's got lots of individual results in there. Each result contains the field data that came back from the search engine. And we just iterate over them. We only get, like, by default, 10 at a time back from Solr, so we don't have to worry about swamping anything or consuming huge amounts of RAM. And we just go through each result, and we say, hey, we want a link. We're going to put our ID in after the docs, and we're going to put our title in right there, and we get a nice, shiny, crappy link. Please don't do this. Please use something better to construct your links. Highlighting is not too much more work. We simply set up this. I'm going to use a quarg stick that we're going to pass in with the ** syntax. You could manually pass these in as just standard quargs in many cases, though Solr likes to break Python syntax by introducing dotted things that get passed as get parameters to URLs. So quargs usually end up ending best in this case. But we simply say, hey, we're going to drop our microphone. We're going to turn highlighting on, and we're going to say, hey, our fragment size is 200 characters. And we run our search as normal, just with the added quargs. And the results we get back will be the same. We get that same results collection with each of the 10 results in there. But we also get this added on additional highlighting property that's hanging out at the bottom of the body. And it happens to have the result and the, it's keyed off of ID. It's really kind of terrible because we're back in the land of XML. But it's possible to get your highlighting results back off. Excuse me. So advanced queries are a piece of cake because basically Solr handles a wide variety of advanced queries just in the nature of it. So using standard parens and Boolean logic, we can construct something that says, hey, it can have world or hello, but regardless of which of those it has to have been created from the beginning of time up until the end of October. Faceting, also really easy. Those nice drill down things that you see in the sidebars of Amazon or nowadays of Google are what's called faceting. And what it comes down to is it just comes down to finding unique values that are popular within the corpus that you have. So for instance, in the slide a ways back, we were going by the site that the content appeared on or the date that it appeared on. Faceting lets us do simple counts to say, hey, the 20 documents appeared a week ago, and a month ago there were 60 documents. And we can give nice counts that show users, thank you. Sorry. Oh, my God. We can give them nice counts saying, hey, this is the relative popularity of this thing that's found in the index. So if you want to drill down from the high level of Amazon.com into grocery, into perishable foods, into bananas, you can. It's a way to categorize and navigate the content that's in a search index. So turning it on is easy. You just say, hey, faceting is on, rather than true like we were handing it before, because consistency, thanks Solr. And we say, hey, we want to facet on a couple fields. We've added onto our documents the author field and a category field. And then we just do another search query. And yet again, same kind of response body for all the results. But we get the facets back as yet another crazy thing at the end of the body. Thank you, Solr and XML. And we just pull off author, which is going to be a list of all the popular authors. Now, there are some caveats when you're doing faceting. Virtually all of the backends we've talked about, or engines, can do some form of faceting, but you have to prepare your data slightly differently. Normally, when you hand content off to a search engine, it will heavily post-process what's being sent. But for faceting, you don't want the content to be post-processed because you might have something like hello worldly travelers become something like hell world travel. And having people facet on hell world travel really isn't that popular. Weird. So you want to be very careful about how you prepare the data that goes into faceting. You also can't reuse those fields for search because they're no longer being post-processed. All the magical inverted index juice and the tech that's behind search no longer applies. So you're going to have to start, again, doing more of the denormalization thing and denorming both a searchable copy as well as a faceted, clean, pristine string format of the data you're storing. Spelling suggestions are a little bit more wordy. Obviously, we're just turning it on. We're setting up which dictionary we're going to use and lots of other delicious parameters that Solr demands. And then, yet again, we get a crazy property back that says, hey, spell check, and it has a list of suggestions. Autocomplete, easy peasy. You just run a standard search. As far as Solr and Elasticsearch and friends are concerned, you're really just searching in a field. The magic, again, comes in when you're preparing data. Much like faceting, you need to take a different approach when you're choosing to try to enable autocomplete. What powers autocomplete in almost all cases is what are called n-gram fields. You basically take a window and you slide it over your data and generate small little fragments. And those fragments become the terms that go into the index. So instead of putting hello world as hello and then another term of world into your index, you're actually passing in something like HEL, ELL, LLO, WOR, yes, I can spell, ORL, RLD. I will pass the sobriety test after this. N-grams take all these unique terms and can now nicely complete, as soon as a user starts typing, what kinds of search results match. And of course, the longer the match, the better the quality of the result. So this matters mostly just in the complete me field is just something, a normal field that we've just placed on our index, and we're just happy that WRL is all the user has entered thus far. So there really isn't a whole lot of magic to make autocomplete work. It's just a space trade-off because you now have a lot more terms that you're going to have to store, and your inverted index is going to be bigger. Don't tell the pyramid guys. They're downstairs. So I wrote Haystack. Haystack works with all the engines that we have been talking about thus far. Whoosh, there's a third-party Zapier adapter, Solr, and Elasticsearch. And basically everything we just went through is on this slide. Tries to just put a nice API on top of all of these things, and with a small settings tweak, you can switch from deploying on Solr to deploying on Elasticsearch, and has some nice facilities for building clean data and storing it and indexing. So I promise that's all the Django I'm going to make you suffer for a PyCon. So now we come back to where are we? We have fast search. It's modern because we can run better queries and we can do all kinds of cool UI tricks to make it more useful. And we hopefully have happy users, right? We have happy users? No? Have any of you seen happy users? So let's talk just a little bit about the future. And again, this is me definitely doing this. Related content is a big deal. I used to work for actually a variety of newspapers, but one newspaper in particular. And we had just finished implementing, updating their whole search stack. And they thought, hey, we're done, this is great. Our search doesn't take hours now to run. But one of the nice things that falls out of using things like Solr and Elasticsearch is that they have a functionality called More Like This. More Like This is exactly what it sounds like. It takes a given document or a given piece of content and can find other documents that are like it. And it can do this because it knows about all the terms that are in that document, and it can find all the other documents that have those same terms. It's a fast, basically set lookup that happens in memory. And what falls out of this is you find stuff that is really, really close but is not the same. And it turns out users are really interested in this. To give a rough metric, they put one More Like This tag on the bottom of their page, and they increased their page views by 175%. So like related content, very boring, very easy to implement, huge wins. No matter what you're doing, I bet some of your users have a use for it. Geospatial search is huge because we're starting to teach computers what the real world means. And it turns out the real world still matters a whole lot to people. So adding geospatial search lets you easily look for things that are around you. Again, this is trivial. Whoosh and Zapier don't really have support for this yet, but Solar's support is pretty good, and Elasticsearch's is just amazing. And it's literally 10 extra lines of code. We're talking about next to nothing. More like this is about 2 extra lines of code. We're talking about very simple things to implement right now. Specialization is one that doesn't get a whole lot of coverage, but it's the idea of these search engines tend to treat everything as roughly the same. If you have a blog post or a comment or a profile or something else, they all get treated as roughly the same. And sometimes having just search through everything works great. But if you can specialize and kind of compartmentalize how they can perform searches, you can let the user have more control over what they're trying to get out of the index. So for instance, you can narrow down to just blog posts. Or if I'm in an archive view of something, I can say, hey, I can preload this search as being within this month's worth of content. And that also plays into contextual search. Another area is indexing things that aren't classical text documents, things like images, music, all sorts of other forms of media, videos, and taking more advanced types of things, converting into something that is still searchable, but is not your classic full text search kind of thing. And for instance, Solar has fantastic content extraction built right in. So you can throw PDFs at it and not think anything about, firing up any report lab libraries or anything else to try and extract content. It can just handle it. Real-time is another big one. I hate trumpeting about real-time because it flies at you from everywhere online. But having up to the minute or up to the second search results can be very, very powerful. And I don't think it's still very much doable right now, though you have to be careful not to swamp your servers or your search engine because of how intense indexing can be. But it's very doable today. And then finding new ways to present search results. We're all used to typical search result pages and like what they look like online or within things like, apps that we use like iTunes or something like that. But finding different ways to integrate search results without having a search box there can be very powerful and interesting. And so with that completes the talk.
We have time for like 3 questions, maybe, or 3 minutes for questions. If anyone has any?
Hi.
Hi.
Really like your discussion about the future, and I'm just wondering, all of this. Have you thought, or has it even came within scope of things like semantic web or something like that?
It does play well into semantic web things, but I don't think there's anything that's built right now to handle like straight up RDF documents or anything. I imagine there are plugins that have been made for Solar and Elasticsearch. So if you can stomach Java, you can easily extend both of their functionality with different search handlers, different components, and is the term they use, and build on other things. So you could build something that handles RDF or can do other SemWeb things, process microformats, all kinds of things. Is that what you're going for, or?
Well, I was just seeing that there's parallels to it. I was just wondering if they diverge in any way, or is that what we're all end up? Are we all coming to that same conclusion, just different paths?
I think it's more along the lines of 2 different approaches to things. I don't really see a lot of people talking about convergence, so I'm not sure I'm the best to talk about that. But I kind of see it as just a different approach to things.
Okay, great.
I'm curious, something I've always wondered about is how stemming works. In particular, you must have different rules for different human languages. So do these search libraries have support for English and French and Finnish and German and Swahili and...
Yep. So I'm sure you all heard that, but the question is, how do these search engines handle multiple different kinds of languages and performing the stemming? So stemming is one of the other parts of the secret sauce of search that just due to time I didn't really have time to talk about. But it's basically the process of finding root words. And unfortunately, the process of finding root words and handling things like stop words and whatnot is very, very painful from search engine to engine and from language to language. There really is not a lot of standardization. You'll find that English stemmers work the best. And as you go through the Romance languages and then into more obscure languages, that support increasingly just goes down to the point of not even being able to handle, parts of the language's grammar and things like that. So it very much is a thing where if you are trying to handle multiple languages, you need to configure multiple different stemmers and you need to look at what kind of results you're getting because it may be really crappy. And like the engines have support for introducing other stemmers if you can write something better yourself or improve on them, but the general state of affairs is less than wonderful. You're going to have much more space taken up, and it's just a multiplier on how many records you have. And the last thing you want to be thinking about is what is the CPU cost to be running this kind of a search query? If it's relatively simple, easy queries, it may not be so bad. If they're running very complex things to do some higher-end analysis, then you really need to make some space. So I'm going to make some assumptions about you, dear audience. I assume, one, that you know Python. I'm going to hope that's not a big stretch. I'm going to also assume that you know just a little bit about SQL and about I/O, just enough to know that, hey, if I kind of know how SQL queries are structured, and hey, I/O takes reading a file off the file system. I'm going to assume that you can kind of figure out words like tokenize, and I'll try and explain some of the other search terminology I use as I go. But if I'm saying something crazy, you should definitely call me out. And I'm going to assume that you want to make your search even better. If you're happy with how things are right now, then don't change it. So, I'm going to warn you. I'm going to say some very hurtful things in a second here, as politely as I can. But know that all of us have been there, well, unless you're Guido, and that this is a process. It's all about making things better as you go. So, without further ado, I want all of you to take a deep breath and steel yourselves for the worst code you'll see yet. It doesn't look so bad, does it? It's kind of innocuous. It's just nice Python. Well, there's some issues with doing this kind of an approach to search. First of all, we're collecting what's presumably a list of file paths, and we're opening them all, and is it just client software and only one person is ever running a search query at a time? Are you doing millions of search queries a day? Having a good gauge on how much load you're going to be placing on your search functionality matters a whole lot in what you pick. Similarly, you want to be thinking about the intended usages. Is search core to what people are doing? Is it the only way to navigate a huge mound of data? Or is it something that's more of an afterthought? Is there navigation in place in the application that already takes care of whatever they need? You want to be thinking about the amount of data. Are you going to have tens of records, thousands of records, millions of records? This greatly affects what choice you make, as well as storage considerations, because each one of those records takes up space. If you have very small records, say for instance, you're just storing tweets, that's a very small finite string with lots of documents. Whereas if you're storing a big corpus of, say, a library or some huge pile of business documents or something else, Thanks. So, the thesis of my talk today is that there are lots of different ways to do search. We're going to see a whole variety of them, but I need to amend this statement because there are lots of wrong ways to do search. So who am I, you might be asking? Who dares say that I'm doing search wrong? My name is Daniel Lindsley. I run a small web consultancy that is in the process of shutting down, so if you need anybody, please let me know. I am a longtime Pythonista and more recently known for what I do in Django. I spend lots of time writing all kinds of different Python things, so it's not just Django apps, but it's what people know me for. I'm the author of 2 applications called Haystack and TastyPie, both of which are Django third-party libraries, but we're not going to talk much about Django today. Instead, we're going to try and attack search from a broader Python perspective. So, what you should know most of all is that I really get excited about search. I love search technology and RESTful APIs, but that's a whole different talk. The most important thing you can do is to pick the right approach when you attack your search problem. There are a whole diverse world of different possibilities of how much you may need to handle or do, or what function your search feeds into. So picking the right approach makes more of an impact than anything else I'll say in the rest of this talk. And there are things that I'll say about higher-end search that may not apply to your use case, and so feel free to ignore them. So, some considerations, or maybe not. Nope, no considerations. Okay, things you want to be thinking about when you start tackling adding search to a product or to an application or to something else. You want to think about the frequency of use. Are you going to be serving thousands of people a day?